Okay, so this next section, 2.4, is about solution sets. So we can actually classify the types of solutions that we get. So when we get a consistent system, we can classify it in two ways: homogeneous and non-homogeneous. So first, let's talk about what a homogeneous system looks like. All right, so this is a homogeneous linear systems. And that just means that our system equals 0. So AX equals the 0 vector. All right, so when we do have that, AX equals 0, where A is a matrix. Okay, so let's say A is an M by N matrix. The matrix we're multiplying by, so if it's going to be M by N, this is going to have to be an N by 1. So this X is going to be an Rn, which means that the 0 vector is in Rm. So it's really good to keep track of the dimensions of what we're working with. All right, so this system, Ax equals 0, is always going to be consistent. So it's always consistent. Why? Because you can always solve it. X equals 0 will always work. Because x equals the 0 vector is always a solution. And so actually we call x equals 0, we call this the trivial solution. So keep that in mind. We're going to use that a lot in the future when we start talking about linear independence. So trivial solution is just x equals 0, something that's always going to work here. Okay, so let's look at an example. We want to find all solutions of Ax equals 0, where we know what A is. So A is going to be a 3 by 3 matrix. And when I go down the columns, I have 2, 1, -1, -3, 1, 3, and then -1, 2, 2. All right, so how do we find all of the solutions? Well, we already know one of them, x equals 0, but what about all of the others? We can, of course, set up an augmented matrix for Ax equals 0. So here's our A. And we're going to set it equal to the 0 vector. And of course, we would go through the work. You're welcome to use MATLAB or something to row reduce really quickly. But I'm going to get it into RREF. And when I do, down the columns, I'll have 1, 0, 0, 0, 1, 0, 1, 1, 0. And of course, these zeros are not going to change on the other side. Now we see, oh, well, actually, we got more than just the trivial solution here. So let's come up with a general solution. All right, so let's start with x1. So I got 0 minus 1x3, so it's going to be negative x3. So we see what our free variable is. Also, we have another negative x3. And so x3 is free. Okay, so let's actually write our general solution in a new way. So instead of just like listing out what x1, x2, x3 are, let's actually write the general solution as a vector. We can do that. All right, so as a vector, the general solution of ax equals 0 that we just solved has the form, okay, remember we're solving for x. So you can do this in one step, but I'm going to do it in 2 steps just because it's clearer to see where things are coming from. All right, so the x we're solving for, we're just going to write this as if it were a vector. So I'm going to draw my vector. In the first position, I got negative x3. Next, I got another negative x3. x3 can be whatever it wants to be, so we're just going to call it x3 here, because the x3 is going to determine what everything else is. So it looks like a vector, but notice that x3 is in common in all of them, so we're going to factor it out. All right, and so this particular form that we have written here is called parametric vector form. And so remember what we had before, just writing the general solution like this was just called parametric form. Now that we've written it so that it looks like a vector, it's called parametric vector form. All right, so what does this mean? Well, that means we can write every single solution for our system, ax equals 0, as x3 times this vector, which I'm going to give a name, calling it v. So every solution looks like this. So all solutions have this form. All right, so note, I'm actually going to stop the video here and pick up in the next video because I don't want to run out of time.